right, cool. I think we're just about ready to get started. How's everybody's morning going? Yeah. Got some good sessions. You hungry for lunch yet? Don't worry, it's close. It's a mere 45 minutes away. And if it helps, I'll talk really fast, although the sandwiches all still come out at the same time, so sorry for that one. All right, so hello everyone. I'm Eli. I'm an engineer at Shape Security. I work largely in making web security products, and so today, because of that, we're going to be talking about secure peer-to-peer browser communication. If anybody's interested in seeing the slides, you can get them from the bit.ly link down here. They're all up on slide deck or speaker deck. And yeah, if anybody feels like tweeting at me and geeking out about it afterwards, you can find me. I'm at Eli Codes on Twitter. Love to hear from you. So let's get started. Secure peer-to-peer. P2P. What does that really mean? First of all, let's kind of break it into a couple of different chunks here. Let's look at the security portion first. So for something to be secure, it has to be confidential, it has to have some integrity, and we have to provide, ideally, anonymity for the people who are using our service. So first of all, what does the confidentiality mean? Well, that means that if Bob here is talking to Alice, that any kind of middle parties in between who manage to intercept that transaction on the interwebs can't actually read and understand what the messages are, at least not easily. On top of that, we have to make sure that there's some integrity. How does Bob, who's sitting here trying to send a message to Alice, know that Alice is really Alice? And when Alice receives that message, it's important that she's able to verify that the message has been signed by Bob, as in nobody else but Bob could possibly have given her this message. This gives her the integrity portion of what we're going for when we're going for security. Finally, and this is a slightly more optional one, normally if you have confidentiality and integrity, that counts as secure. But if you want to take it a step further, we can provide anonymity. And that means that anybody who sees the transaction coming through in the middle can't tell that it's necessarily Bob and Alice who are talking to each other. So next, let's take a look at the peer-to-peer portion. I mean, as many of you know, most of the web works kind of like the diagram over here on the left. We have a lot of different users, they're all spread out across, and they're all talking to one big central server. Even if two of those users are talking to each other, all their messaging goes up, comes up through our web servers, does whatever our app has made it to do, and then comes back down to the person. So if Bob and Alice were going to use a traditional service, be it Facebook or anything else, it's going to go up, you're going to talk to the server will realize that Alice deserves the message, handle the signaling, and send it back down to Alice. On the other side, if we're doing peer-to-peer networking, well, that makes things a little bit simpler. It's kind of like how the internet works if you just like walk up and you're like, sweet, I'm going to talk to Alice, I'm going to log into my computer, and my computer points directly towards Alice. And this is really cool. It gives us a lot of like sweet benefits that you don't necessarily get or are hard to get when you're using the traditional network. We can get near real-time latency. There's only like 2, 3, 4 milliseconds. This means that if you want to make a game or something like that, if you want to have the systems propagate between Bob and Alice quickly and for them to be able to really have near real time, if you want to do some kind of first-person shooter or some kind of action-y game, it's very helpful to have that low communication latency as they're going back and forth. Also, if we skip going up to the server and back, your server doesn't have to handle nearly so much bandwidth. So if they're sending big videos or pictures back and forth, as long as they go directly from person to person, your processing power is lightened up so that you can focus on the important things like making sure Bob and Alice can easily connect and things like that, and letting their computers themselves, which are really the only ones who care about the content being sent back and forth, can actually communicate back and forth. Also, as kind of all of these things are pointing towards, you get to use those shiny brand new MacBooks that all of your users are doubtless using, and this way you get to save yourself some bills when it comes to running all of your infrastructure and things. You can have a much smaller infrastructure if you're making sure that all of the heavy-duty images, pictures, things like that are actually getting sent peer-to-peer instead of having to send them up through your server and back down. So a really cool tool that we can use for this that was released recently, and I'm sure some of you have used it, and if you haven't, it is really sweet. It's WebRTC. There's a whole bunch of helper libraries that will help you kind of step along through. For the purposes of this talk, we're going to be talking in the context of SimplePeer. It's a GitHub project by Feroce. It's very cool. It basically turns WebRTC and the connections and signaling that you'd use in that, and you can basically do it in a very simple kind of event-driven manner. So here's a quick code demo that basically takes what would be a new SimplePeer. All you've done is acquire Feroce's project. It's up on Node, pulled it in, and basically, we make a new peer. And then all we're doing here is we're just adding these on listeners. There's like an on stream, there's an on connect. All of these things have fairly simple functionality, but in this case, all we had to do was listen for the on stream, point the stream object that we received and put it into a video HTML like div, and we're ready to go. Suddenly we can have live video coming from one computer to another with really little work on our part. So let's walk through how we would make that WebRTC connection work. Basically, it all starts out with a handshake. If Bob wants to talk to Alice, Bob and Alice have to somehow establish between each other the information for where's Bob in the world, where's Alice in the world, what are their IPs, what kind of proxies and things are they going to have to push the data through. This is all done via something called they have to pull an ICE server, and that basically gives them, from an outer perspective, like where Bob would be, Alice can send it up to this, they'll say, oh, okay, this is what your IP is and things, and then they have to pass it off. But that's not covered by WebRTC, so we have to handle that kind of things on our own. An easy solution that a lot of people use is they'll do signaling through probably like a WebSocket or other kind of server like that. So, Bob and Alice will go, they'll signal, they're like, here I am. Bob will say, here I am. They'll both send up the IDs of the opposite person they're looking for, so Alice will have her specific WebRTC ID. Bob will have his specific WebRTC ID. And it'll go up, they'll send back down, and then basically when Alice receives Bob's ID along with enough connection information, they'll start to establish a few more of these connections. So they can set up their media connections and get media data going back and forth across those channels. And they can set up a data connection which uses SFHTP, I think. And basically that'll let them send kind of more reliable messages back and forth in data. You can send files this way. It's very cool. But that whole process, how secure was it really? So we just went out, we basically threw some things up towards a WebSocket and then crossed our fingers and hoped everything worked out. So let's start to break down where some of the issues we have that we might have to look into here are going to be sitting. So the first, obviously, is that we need to make sure that when we're designing our signaling so that we can get that handshake going between Bob and Alice, that nobody's actually able to listen in between. So it's all great if Bob and Alice can set up their communication, but if they want any kind of anonymity or anything else, leaving this in kind of an open forum kind of state isn't a really good idea. So, and also, on top of that, we really want to try to avoid kind of some of the more dangerous attacks. So WebRTC does employ some encryption just out of the box. It'll make sure that your media and your data channels are encrypted back and forth. But because they don't protect this initial signaling, if you can set up a man-in-the-middle attack, which is to say, for some reason, our WebSocket server has been compromised, or maybe there's a bad actor somewhere in between in one of the signals, if they can step in there, they'll be able to actually pull in when Bob sends out this is Bob's ID, this is where Bob lives, grab that, store it, replay it out so that Alice also gets it, and then basically they've established themselves in the middle of this handshake as it's starting to go on. Once they've done that, they actually have the power that since they can get all of the contextual information going back and forth, including some of the keys and things that will be used to encrypt the data, they can actually start to then listen in on those secured data lines and things if they can manage to insert themselves between those as well. Basically, the way to picture this is that Bob thinks he's talking to Alice, and Alice thinks she's talking to Bob, but really Bob's talking to our bad actor here in the middle. The bad actor then replays everything after recording it or doing whatever he wants to over to Alice and vice versa. So it's kind of like playing telephone between two people, except there's actually a third person in the middle that neither of you knows about. So what's the solution? Well, I mean, you'll probably think it's pretty obvious. We just have to make sure that we encrypt everything. So we want to make sure that when they send up that initial handshake, when they're actually like passing this information back and forth, that we're encrypted and we're safe. And we can do that fairly easily simply by using PGP. So PGP, for those of you who aren't familiar, is a web security format that stands for Pretty Good Privacy. And we're just going to kind of walk through how kind of that would go. So basically in PGP, Bob and Alice, it's a two-key encryption system. So Bob has two keys, his public and his private key. Alice also would have a public and private key. So if Bob's sending over to Alice here, he would generate a random key. He's then going to encrypt his data using this random key. Then he'll encrypt the key he used, the random key that he just generated, using Alice's public key, usually via RSA or elliptic curve encryption. Then he's going to package both of these two up here, so he'll take his data and his encrypted key, turn it into his message, and send it over to Alice. Alice, when she receives it, she's going to get this message. She'll pull out the encrypted key. She'll decrypt that using her private key, so anybody can know Alice's public key, and it's completely fine, but only as long as only Alice maintains the ownership of her private key, then while anybody can encrypt something with her public key, only Alice will be able to decrypt it from the other side. So then once she's taken this down, she's decrypted the random key that Bob generated, then she can decrypt the message and everything is good. Now, this is really cool for kind of one particular reason, well, a couple. First of all, we have the public and private keys so that anybody can send an encrypted message to Bob, but only Bob can decrypt it, or vice versa. But also, because we're using this random key, this gives us something called forward secrecy. This means that even if somebody intercepts this encrypted message, and even if they manage to get the key this time, the next message that Bob sends to Alice, they're going to have to go through all of the work of guessing that key all over again. So there's a couple of different techniques that you can use, like PGP supports RSA, it supports ECC. There's a couple of other encryption formats that you can use, but what's interesting about this is that for things that we really want to make sure we can trust, RSA is probably a better option, but because it relies on two very large primes, and those aren't easy things to calculate, in some cases, for instance, if we're using a key for only a very short period of time, elliptic curve cryptography can actually be more useful. That's ECC. And that's because it's much, much faster to be able to compute or generate two different keys. So what are we going to use as we're out here in the browser? There's not that many cryptography libraries that I know of in JavaScript. But luckily for us, there is at least one, and that's KBPGP. And so that's a great little library. It's kicked out by the same guys who make Keybase.io, which we're going to talk about a little bit later. And we can run it both as a node dependency, or it also can serve up just as a raw dependency, and we can plug it into any of our websites and things like that, which is awesome because really we wanted to get secure communication between our browsers, not just between our node applications. So let's talk a little bit about KBPGP. So what kind of things does that give us? Basically, KBPGP lets us do anything we want with PGP. It gives us key generation, which is important if we want to generate keys on the fly. It gives us encryption, and kind of obvious gimme. It gives us decryption, And it gives us verification. This means that if Bob and Alice are sending messages back and forth to each other, that when Bob sends a message over, Alice can actually verify that it was in fact Bob who sent this message. Even if Bob doesn't encrypt this message, he can just sign a message and then put basically a cryptographically signed hash at the bottom of the message. And so even though the message is in plain text, Alice can look at it, make sure that it's from Bob, and make sure that nobody else has tampered with it along the way. So what's it look like to generate keys? It's actually really simple. I mean, this is about 4 or 5 lines of code. It's a little bit complicated because as key generation is a little bit slow, we have to use callbacks to kind of offset some of the performance issues that you would have otherwise. We don't want our whole application just to stall out while we're trying to generate our keys. But basically what we're doing here is we're pulling in KBPGP, and then we're having it just generate a couple of RSA key sets for somebody with the name of Bo Jackson. Encryption, once you have this key pair, is also similar as simple. All it is basically you set up a couple of parameters like your message and who you're encrypting it for. That encrypt for is actually basically Chuck would be standing in for the public key of Chuck that we want to encrypt to. And then we use the KBPGP box method, which wraps it all up and will return us out with a what they're calling an armored string, which is basically a buffer, which will give us the armored string, which is of course like a stringish object or a buffer, so that we can kind of feed things out in more of a stream if that's something that we're trying to do. It also means that because we can handle the buffers, we can encrypt things that are bigger than just a simple text file. We can do something like a video or a picture or something like that. So if Alice were to receive this on the other end, it's not too hard on her either. Basically, she would look at her keyring here. This is something that you would store any of your number of keys that you've generated. So Bob's public key, maybe she's also friends with Adam and Bill and Jennifer. They would also have their public keys stored on this keyring, which is something that KBPGP looks at just so that when Alice receives a message, instead of trying to verify, obviously it's encrypted for her, but then to check the signatures and things like that, we have to be able to check against the different public keys of people who are there. So we'll go through, we'll grab a key from the ring, decrypt it, and hopefully everything's good. Things might look a little bit interesting right down here, where it has the literals to string call, and that's just because it doesn't, KBPGP doesn't give us a straight string object, because it has its support for buffers as well, but will actually give us something more like a character array. So something to pay attention to, how are we going to keep these shiny new keys that we just generated secure? And the answer to that is really, you as the app owner don't want to be overly responsible for the keys. There's a lot of different things called public key registries. My current favorite one is something called Keybase.io. And basically what that does is it stores verified up against your different social media accounts, be it your GitHub, your Twitter, Bitcoin, Reddit, websites even, as long as you have a specific tweet that has some kind of a signed hash for it, Keybase will actually go out, check that, and so now everyone on the world who wants to send me encrypted messages can actually look me up via my Twitter ID, Eli Codes, and then Keybase will handle checking back through the history of my tweets and see, oh yes, Eli Codes does still have this public key, and so it makes it really cool and easy for things to do. They also release it as both a command line tool, which is nice because it means you can run things in a very secure environment and keep your private key where it should be, on your own computer and not going anywhere else, and an open API so we can do AJAX calls out to that as any of us as app developers want to, and then we can pull in people's public keys like Alice's or anybody else who's registered to the site. So then we have to figure out kind of where are we going to store these keys. So our Keybase IO key pair, which you've generated and like run through. That's going to say you're going to have your private key, hopefully locked down securely inside your own device, and then you're going to have your public key out and accessible via this CORS API that you can use out on Keybase IO. On the flip side, we're going to have to generate some kind of a session pair because we don't want, as the app, when Bob is talking to Alice, to actually have some kind of access to the private key there so that we can do the encryptions inside the browser. So for every Bob and Alice transaction as they come in, we're going to have to generate them a session key pair. This pair is going to be a very limited session length, probably only for the length of the time that they would want to talk to each other. And the trick here is that we're going to have to link it to our Keybase IO pair, because remember how we were talking about trying to get that integrity going so that Bob knew who Alice was and Alice knew who Bob was? Well, that's not going to work, and how can they trust some randomly generated key we've put on the app unless we can link it to something much more concrete and much more queryable, like the Keybase IO? So there's a couple of different ways we can do it, but probably the easiest way we can register somebody is that we can use an authentication token. A lot of you guys who've done any kind of login pages or things like that are likely very familiar with authentication tokens. Basically what it is that after somebody logs into your site or signs in, like, they're going to give you a username and password, then after that you have to somehow store that state and keep them so that for the next transaction and the transaction after that, as they walk through your app, then you're going to be able to verify that they are who they said they are. So it's a very similar concept here as we're trying to set up these PGP key pairs as we go through. So, and here's just a couple of the different things inside here. We're going to walk through this a little more carefully once we've seen how we can use it. But you have to have an identifier. It would be good if we had a public key so that when somebody signs in, we can give the public key, say Alice's public key, in here and keep it locked in. And then we're going to have expirations, a nonce to make sure that it doesn't get replayed over and over again and things like that. So let's see how this might kind of work in a more live setting. So if Alice is coming up to our site and she wants to do some kind of a request, basically she's going to reach out and ask for the web page. Web page will come down and it'll say, oh, you're a brand new user. It's going to generate some new keys for Alice. Next, it's going to ask Alice to generate and upload some kind of that secure token that we were just talking about. This way, basically, Alice will go. She'll pull down some kind of a JSON blob. It'll ask her, please encrypt this, on her own device. Her computer can then encrypt it, sign it with her Keybase IO, private key, and send it back up. And now we have something that's verified where we have both the key pair that we just generated along with a signature from Alice's original Keybase IO constant safe key so that we have both a session and the long-term keys so we can verify back and forth. So now let's look a little bit more at what that authentication token has to do now that we've kind of seen how we might use it. So first of all, we have our ID. This would be the ID that Alice would use probably for the Keybase IO, right? This is something that you can get very easily from her. Is she logs into the site and suddenly you're going to be like, all right, who are you? Give me your Keybase IO ID. Very simple. So then after that, we need the public key. So this is the public key that we actually generated as the app to just help her out so she can have her secure communication sessions with whoever it is she's trying to talk to. Expirations, as in we can't use this token past some kind of date, as well as we can't use it before the NBF, any kind of date as well. So this way we can very carefully time window when this token is actually going to be valid. Next is kind of the more interesting part, is we can have a secret in here. And this secret could actually be, we can set for ourselves because we can do KBPGP encryptions and key generations both in Node and also in the browser. We can have our application have its own key pair. And so what we can do is to make sure that Alice knows that she's using the site that she thinks she is, then we can actually encrypt this nonce that we're showing up here just below it into a encrypted message that's been encrypted with the private key of the website. And then when Alice decrypts this and sees that the nonces match up, she can feel secure in knowing that the website is the actual origin and place that she wants to be talking to, as well as that they have, continued to maintain her trust. I just put down here in the bottom for kind of reference that one way, and while not ideal for the user friction, is that we could literally just have her copy paste something like this out of the browser, run it up against this in her command line, and we would have a fully signed and encrypted authentication token that Alice can use. So now that we have this token, it would be really great to see where we can put it. So Alice signs in, she's registered, she has her token, she wants to talk to Bob. So now when we do that signal up to Bob, say, hi, this is Alice, etc., we can actually encrypt it. Well, we can send it out with this authentication token attached into it. This will let us do kind of whatever we want. So now when we pass this through, Alice can have her signaling packaged up and encrypted using her private keys. And when Bob receives it, he can say, oh, great, all right, this came from this, randomly generated key set. And look, once I've decrypted it, I can actually see that the token comes from Alice. He can then query Keybase.io, which, because it has all of this AJAX support, Bob can just go out and say, oh, okay, is Alice really who she says she is? And he can verify it against her Twitter, he can verify it against her website, he can verify it against her GitHub. And this means he can kind of realize exactly who she is. So now that we've kind of set this up, now our picture looks, well, a little bit simpler. Basically, we've managed to create a public, two sets of keys here. We have our session keys, which we can use to fully encrypt the media and data that they want to send back and forth. We've managed to mitigate any kind of man in the middle because we have these secure tokens that are getting passed through, which they're not going to be able to encrypt. And even if they do step in and intercept that token as it comes passing through, it doesn't really matter because all further communication is going to be locked into this public key. And if they tamper with it, because we can sign the message and make sure that when it gets to Bob, Bob can actually verify it against the Alice signed cryptographic hash that it hasn't been messed with, they can't change the public key on you for the session key that you're trying to pass along. So after that, it's pretty great. We can have a slightly more secure encryption scheme, and actually, fairly interestingly, we managed to get Alice and Bob to both register up onto the site without having to use any passwords at all, but that's kind of another topic. So what's next? I don't know. Profit? I think there's a lot of different things you can kind of go with it from here, but because I just threw a whole lot of information at you, I'd kind of like to open it up to questions and kind of start more of a discussion from here on out. So let's take it from there.
Do you have a suggestion for a lower friction way to have the users like Alice generate the token?
Yeah, great question. So he's asking, do I have a suggestion for a lower friction way for users to generate that token? And so Keybase and KBPGP, it would be very simple just to give your users a very small modular app that they could use that would probably alleviate a lot of this friction. I know as developers, using the command line tool is fine and easy, but for the average user, just a little kind of GUI program would probably be the best bet that I would suggest. So the question is, can you use this kind of technique with the WebCrypto API? And my answer without knowing all of the details on the WebCrypto API would be yes, you should be able to do something in kind of a similar fashion. Well, okay, it's as provable as it would normally be. So say if we're here and, I mean, you definitely put yourself more at risk, like having, if you want to look at this public key, if we encrypt it when it goes over, like if we already know what Bob's public encryption key is, we can hide all of that data up for him. We can package it up one more time. So we can hide things a little bit better, but it's true. If you want to like query all of the keybase IO things and like check a large number of different users, you could probably narrow it down once you see something that matches.
I might not understand it fully, but do the interface have to create a keybase IO account, or is the application itself building something using keybase IO?
Right. In this example, you would have to have a keybase IO account, which is more just that you've used their site to create this public-private key for yourself. But that isn't to say that keybase IO is the only like public key registry out there on the internet that you can use. If you wanted to use a different kind of service, yes, you'd be able to do that, but you do need something that people can query against to like make sure that they have this kind of ID. If it helps, I know Keybase is it's very simple for users to walk through, and it probably wouldn't be like untoward burden on somebody to say, oh, if you want to use this secure messaging app or whatever it is that you're trying to do, file transfer, to like help them step through that. And I think you can actually have them sign up via the API and not even have to redirect them over to the site.
So what if the keybase IO being hacked?
So that's always a risk. If Keybase IO had been hacked and they'd been breached, hopefully, as this is kind of what they do, like you as the app developer would have been alerted, but it's true. Those, any currently existing sessions would potentially be compromised, mostly just in that we would no longer be able to verify for sure that Alice was actually in fact Alice. But as we're only using Keybase IO for things like starting the session and kind of verification, once as Alice passes over, Bob's going to say, oh, okay, sweet, this is in fact Alice. After that, the rest of the session is actually still locked into those other session generated keys that we made. So it would be bad. It would actually be very bad. That's what kills public key registries, is if they get hacked, you have to make a new key. Basically, if they get hacked, all of your users who are relying on their Keybase IO keys would have to make a new key before they could reliably continue.
So if it's secure app, assuming all communication through HTTPS or RADA and encrypted with TLS, how would that factor in? Do you need to encrypt everything in this case?
So in things where you can establish a man-in-the-middle attack, the HTTPS and things, if they've managed to compromise, say, your signaling server or something like that, while HTTPS, you should definitely be using it as much as possible. As a security guy, I fully support it. But you can get around that. I can fake the HTTPS certs a lot easier than I can probably break one of these PGP encrypted keys. All right. If there's not any more questions, thank you so much for listening, guys. I really appreciate it.